Hello friends, welcome to the channel Physics by IITians. Today we shall discuss a very important topic, that is Raman scattering or Raman spectroscopy. And this topic is very important because it has huge area of applications in research. So I request you to understand the topic very deeply, and also whenever I face any interview and I tell them that please ask me any questions from spectroscopy, they usually start asking what is Raman spectroscopy, and then they start the other questions. So I request you to watch the full video. Let's start. Today we shall discuss about the origin of the Raman scattering or Raman effect. Then we shall discuss about the Stokes line, anti-Stokes line. We shall understand its explanation. The explanation will be based on the classical picture and the explanation based on the quantum mechanical picture. Then we understand the intensity difference between the Stokes line and anti-Stokes line, and why is it so, why there are intensity differences between the two lines. And then we shall compare the Raman spectroscopy with IR spectroscopy or vibrational spectroscopy. So the infrared spectroscopy or rotational spectroscopy I have already finished, and you all know that the origin of the infrared spectroscopy or rotational spectroscopy is the change in dipole moment. The change of dipole moment due to the permanent dipole, or it can be due to the induced dipole, but it is necessary. But however, the homonuclear diatomic molecules like H2, O2, N2, they neither possess the permanent dipole moment nor induced dipole moment due to their vibration or rotation. So, they are IR inactive, rotational inactive. So, what to do? How to study their structure, or what is the tool to study their structure? The answer is the Raman spectroscopy, and we will learn the origin of the Raman spectrum and its application. So what is Raman effect? The Raman effect is the inelastic scattering by molecules, and that was discovered by Sir C.V. Raman in 1928, and he was awarded Nobel Prize for this fundamental work in 1930. Now what he have done? He had done that what he observed, when a parallel beam of monochromatic light goes through a gas or liquid or transparent solid, a part of the light is scattered in all directions, and the scattered light contains exactly the same wavelength as the incident light, then it is called the Rayleigh scattering. And then apart from the same wavelength, that is apart from the Rayleigh scattering wavelength, the scattered light also contains some weak additional lines, and these additional lines was first discovered by Raman and his collaborators, and this is known as the Raman effect. What are the important features of Raman lines? The Raman lines are independent of the wavelength of the incident light, but it depends on the nature of the scattering substance. So, for different scattering substance, the displacements of the Raman lines from the incident line are different. Thus, the displacements are characteristic of the scattering substance. So, it is independent of the wavelength, that is incident, rather it is dependent on the molecules or characteristics of the substance. So it is a fundamental effect which can produce the results of the properties of the substance. So the scattered line contains displaced lines both on the sides of undisplaced line, and the separation in both cases are the same. Look here, suppose we are considering the Raman spectrum here. So here we are observing the three lines. Suppose we are taking it as one line, first, second and third, and look here, the first, if you take the middle line, then it has the same frequency as the incident one, but there are some shifted lines, and the shifting is the same on the both side. So amount of shifting is same. So it is on the left hand side also, it is on the right hand side also of the Rayleigh scattering, and these lines are the Raman's lines because these are shifted lines. Now we divide these Raman lines into two categories. One is where the frequency of the scattered light is less than the frequency of the incident light, and that is called as Stokes line, and another line where the frequency of the scattered light is greater than the frequency of the incident light, that is called anti-Stokes line. So That is all for the understanding of basic definition of the Raman scattering. And now the intensities of the Stokes lines are higher than that of the intensity of the anti-Stokes line, and we will also understand that. Now we should understand what is the reason behind the Raman effect. So at that time there was one theory, that is classical theory. And what is the classical theory of Raman effect? Let's understand it. When an atom or molecule is brought into an electromagnetic field, like the atom or molecule, the electromagnetic light field, that is in form of light, is incident on that atom or molecule, what will happen? An electric dipole moment mu is induced in the system, and the magnitude of the induced dipole moment is proportional to the incident electric field, that is mu equals to alpha E, where E is the incident electric field and alpha is the polarizability, and polarizability is the property of the system. If you don't understand what is polarizability and how the dipole moments are changing, I request you to watch that video, that is the physics of dielectrics. I have described here in details. Okay, so what will happen when there is an mu, that is alpha into E, where alpha is the polarizability and mu is the induced dipole. Now the direction of the mu or the direction of the induced dipole is not actually coincide with the direction of the E. You can think that the mu is at the same direction, along the same direction as E, but it is not in general case, because if you don't consider the isotropic molecule, that is isotropic means the spherically symmetric molecule, in that case only the mu, that is induced dipole moment, will be along the incident electric field. But otherwise, for any general case, the non-isotropic molecule, the direction of mu does not coincide with the direction of E. So what will happen? So mu alpha is a tensor quantity. It is not a vector. That is, it can have total 9 components. That is, along x it can be alpha xx, alpha xy, alpha xz, and y alpha yx, alpha yy, alpha yz, and alpha z component can be written as alpha zx, alpha zy, alpha zz. That is, alpha you can write in terms of matrix, where the row, first column will be alpha xx, then alpha xy, then alpha xz, then alpha yx, alpha yy, alpha yz, then alpha zx, alpha zy, alpha zz. So what will be the change in dipole moment, that is mu x, due to the change in the electric field or due to this incident electric field. So mu x can be written as alpha xx ex plus alpha xy ey plus alpha xz ez. Mu y equals to alpha xy ex plus alpha yy ez plus alpha yz ez. Mu z is alpha zx ex plus alpha zy ey plus alpha zz ez, where e square equals to ex square plus ey square plus ez square. Look here, suppose the incident light of the frequency of nu naught, and electric field, incident electric field can be written as E equals to E naught sine 2 pi nu naught t. So what will be the dipole moment? So induced dipole moment mu will be alpha into E, that is alpha E naught sine 2 pi nu naught t. Now look here, if this is oscillating, because electric field is oscillating, so mu dipole moment is also oscillating. Now according to classical EM theory, the oscillating dipole or the dipole will oscillate with the frequency nu naught, or oscillating dipole can generate electromagnetic radiation, or it can generate the same frequency as the oscillation. And what is that? This oscillating dipole radiates with the same frequency of oscillation, and this is the Rayleigh scattered light, or this is the Rayleigh scattering phenomena. Now suppose if the molecule vibrates, that is the internuclear distances are changing. So due to this interdistances nucleuses are changing, that is alpha xx, alpha xy, alpha yz will also change, because it depends upon the orientation of the molecule. So due to its rotation of the molecule, due to the vibration of the molecule, the orientation of the polarizability, the orientation of the molecule will be changed, and the polarizability will be changed. So there will be change in polarizability. and this change in polarizability will give rise to the Raman scattered lines. How is it so? Let's look for the vibrational vibration first. Okay, so suppose the molecule is vibrating, so mu v, that is induced dipole moment due to the vibration, is alpha into E, where alpha is the change in polarizability due to its vibration. So you simply calculate it. The alpha will in the form of alpha naught v, that is the uh, equilibrium position of at the molecule, and the little perturbation term, that is alpha 1 v sine 2 pi nu naught t nu v t into E naught sine 2 pi nu naught t. So you calculate and you get that mu r, that is the induced dipole moment, is equals to alpha naught r E naught sine 2 pi nu naught t, that is the alpha naught is this is the nu naught, that is it is alpha naught is vibrating with the nu naught frequency. The nu naught is that frequency which is exactly equal to the incident frequency. And you also know here, look here, that alpha has also this term, that is cos 2 pi nu naught cos 2 pi nu naught minus nu vt minus cos 2 pi nu naught plus nu vt. So this is the in alpha naught, that is the polarizability that is oscillating with the incident light, and this is the polarizability that is oscillating with the modified intensity of the light, or with the modified frequency. This is not exactly nu naught, but it has components like nu naught minus nu v and nu naught plus nu v. So there is the oscillating frequency is different from the incident frequency, so it will emit radiation with a modified frequency. And if you find this change in mu, that is change in dipole moment due to the rotational motion, then you find out mu r equals to alpha naught r E naught sine 2 pi nu naught t plus alpha naught alpha 1 r by 2 E naught cos 2 pi nu naught minus 2 nu r t and nu cos 2 pi minus cos 2 pi nu naught plus 2 nu r t. Means what does it mean? I am showing you the equation just because from the equation you can understand the physics here. Look here, this mu r, that is the induced dipole moment. It has component the alpha naught, which is exactly oscillating with the nu naught frequency, that is the undisturbed or unperturbed frequency, that is exactly equal to the incident. It is the relay frequency, and these are the different frequencies. These are responsible for the Raman light, because these are vibrating with different frequencies, and this will give us a different line that is not match with nu naught, that is incident frequency, but that will be shifted from nu naught, and the amount of shifting here, nu naught minus 2 nu r and nu naught plus 2 nu r. And for the vibration case, it is nu naught minus nu r and nu naught nu minus nu v and nu naught plus nu v. Okay, so this nu r is the frequency of the rotation, and this nu v is the frequency of the vibration. So the induced dipole moment not only oscillates with the frequency nu naught, but also other displaced frequency like nu naught minus nu v and nu naught plus nu v in case of vibration. And for rotation, the displaced frequencies are nu naught plus 2 nu r and nu naught minus 2 nu r. Okay, but this is quite good. The classical explanation we can get, the understanding about the Rayleigh scattering, the Raman scattering, the Stokes line, anti-Stokes line, but classical explanation fails somewhere, and because it doesn't provide information about the intensity for both the lines, and thus inadequate for the explaining the experimental spectrum. So what is the experimental spectrum? We will learn it. So we understand that here the classical theory cannot tell us the intensity difference of the Stokes line and anti-Stokes line. So we should need more fundamental explanation, and we find out the quantum theory of Raman effect. So what is the quantum theory of Raman effect? So let us consider for a system that is E naught, and E naught is its ground state, and the vibrational states are V double prime equals to 0, 1, 2, 3 are the vibrational states of the ground electronic states, because there are within one electronic states there are several vibrational levels, and within one vibrational state there are several rotational levels. So we consider here first the E naught is the ground state, where V double prime are the vibrational states of the ground electronic state, and the light frequency that is incident has the frequency of nu naught. So there are three cases may arise. Let's understand the diagram. So suppose first the molecule, case 1. The molecule absorb the light of frequency h nu naught and go to the vibrational state. Now the vibrational state is created by the light and molecular interaction and exists as long as the light exists. So it is not the eigenstate of the system, but is a linear combination of all eigenstates of the molecule. Thus the lifetime of this virtual state is very small, and now the molecule will back to the ground vibrational state, that is V equals to 0, and will emit the same frequency as nu naught, and this is the relay scattering. Here suppose this is our ground state, electronic state, and this is the virtual energy states. Within ground electronic state there are different several vibrational states, 0, 1, 2, 3, 4, these are all vibrational states. Now there is an incident frequency with the wave length lambda naught or frequency nu naught. Now any molecule atom which is at the ground state, it will get excited and it can jump to the vibrational energy state, and it can again come back to the V equals to 0 level, that was its initial position. So the scattering is elastic scattering because there is no net transfer of energy. The incident radiation will be exactly the same as the scattered radiation. But suppose if the atom or molecule, if the molecule is at V equals to 0 state initially, and then it, after the radiation, incident radiation, it absorbs the incident radiation and it goes to an higher excited state or the virtual energy state, and then it come back to lower state after some time, within certain time, and it doesn't come back to the its initial state V equals to 0, but it comes back to another state, that is the higher vibrational state, that is V equals to 1. Then what will happen? The incident amount it has taken will not be the scattered amount, because it will, here look, it will have some energy to stay here, and the energy will it will get from the incident radiation. So the scattered light will have lower frequency than the incident light. Now suppose the third case, if the initially the molecule within V excited vibrational level, it is not V equals to 0 state but at V equals to 1 state, then the incident light it absorb, it can jump to a virtual energy state, and then it come back to V equals to 0 level. Now it will radiate its own energy also. So the frequency that is incident and the frequency that will be scattered, that will be not equal, and the scattered light will get higher frequency, because it will also take some an amount of energy from of this state energy difference. So look here, from the Raman scattering or Raman spectra, you can directly find out, or you can directly measure about the information of the vibrational levels or the energy difference of the vibrational levels, and it is independent of the incident light, because it is dependent on the substance, it's dependent on its vibrational levels, it's not dependent on the incident energy. That's why it is so important that it can tell you about the vibrational structure, about the rotational structure of a molecule. Okay, so that is the importance of Raman scattering. Now we discuss about this, why the Stokes line are higher in intensity than the anti-Stokes line. These Stokes line are the lines where the scattered light frequency is lower than the incident light frequency, and the anti-Stokes line where scattered light frequency is higher than the incident frequency. So we should understand first what will be the population at these different vibrational states. So we should follow the Maxwell Boltzmann law, that is in V, that is the population at V level will be n naught e to the power minus E by kt, minus delta E by kt. So the origin of the anti-Stokes line from the higher vibrational levels will depends on the population. Why? Because the population is lower in those states than the ground vibrational levels. So ground vibrational level, that is V equals to 0 level, will be populated at the normal room temperature than the other levels. So here from the diagram you can understand the most of the molecules are populated in the V equals to 0 state at the room temperature. So they will be excited and they come back to an higher vibrational state and it will give you the Stokes line. But at room temperature there will be very less amount of molecules that are present at the V equals to 1 level or higher vibrational levels. So this scattering, that is anti-Stokes line, will be lower. But if you increase the temperature of the substance, then the higher vibrational levels also be populated more and we can also get anti-Stokes lines, and the anti-Stokes lines will be prominent at higher temperature. And this is also an interview question, and they will ask you definitely that why we get the Stokes line more intense than the anti-Stokes line, and you certainly have to answer that the population at the room temperature for the lower vibrational state, that is ground vibrational state, is higher than the excited vibrational states. That's why we get the Raman scattering, that is the anti-Stokes line, Stokes line are more intense than the anti-Stokes line, and hopefully you understand from this diagram also. Now we should understand what should be the selection rule for the vibrational Raman transition and the rotational Raman transition. For the vibrational Raman transition, delta V equals to plus minus 1, and the parity selection rules for the Raman transitions are symmetry to symmetry and antisymmetric to antisymmetric. But on the if you count for the infrared spectroscopy, the transition will be of the opposite parity. Here the symmetric parity or the same parity, that is from symmetric to symmetric or antisymmetric to antisymmetric, this transition can happen. But in case of the IR spectroscopy, the transition will happen if the initial state and final state have opposite parity states. So the IR spectroscopy is the complementary of the Raman spectroscopy. And it is also a very important question that how IR spectroscopy differs from Raman spectroscopy. And we should know what will be the selection rule for the rotational Raman transition. The selection rule is delta J equals to 0 plus minus 2. So if you find out the wave number, that will be Fj plus 2 minus Fj, that is 6b plus 4bj. So the rotational Raman spectrum, the first undisplaced lines are 6b and the separation between the other Stokes and anti-Stokes lines are 4b. Okay, so look, this we get that the first line, that this is the undisplaced line and these are the Stokes and anti-Stokes line. Now we understand with an example how to understand that there is a Raman scattering or there is an IR scattering, or there is a IR spectroscopy, or it is the IR line or vibrational line, or it is a Raman active line. So let us take an example of carbon dioxide, CO2. So the carbon dioxide molecule is a triatomic molecule and it has three modes of vibration. And what are they? They are symmetric stretch, asymmetric stretch and bending. Suppose this is the symmetric stretch, both are expanding or extending or stretching. This is the asymmetric stretch where these stretchings are opposite to each other. One is compressing and another bond is stretching, and this is the bending. Now let us consider the symmetric stretch first. So symmetric stretch, here the stretching will be along this side for this CO and O, between this CO and O, and along this side for this C and O molecule. And the stretching, at the stretching, look here, it is the ellipsoid, the charge configuration of the CO2 molecule. And this overall charge configuration, or the charge ellipsoid charge configuration, we are here because we don't consider the uh, spherically symmetric charge distribution. We have to consider the ellipsoid charge distribution because the polarizability will change with this configuration, and with the change in polarizability we can get only the Raman scattering. So here, look here, during its stretching, the polarizability ellipsoid is changing, or polarizability of the molecule is changing, so it is a Raman active mode. Now if we take the asymmetric stretch, here, look here, the asymmetric stretch, the polarizability of the ellipsoid is not changing, but the dipole moment is changing, because whenever during its asymmetric stretch, the dipole, this is the dipole moment of this particular bond length is not same as the dipole moment of this particular bond length. So there will be a net dipole moment that is non-zero. So it will give you a IR mode or IR active mode. Now if you suppose the bending mode, the bending mode also, you see here, there is no change of polarizability because there is no change in the configuration of the ellipsoid. It remains same, but there is a change in dipole moment, sometime this way or sometime along this way. So the dipole moment is also here, first the time there is no dipole moment, but there are induced dipole moment or the change in the induced dipole moment, and it will certainly lead to the IR active mode. So I hope you can understand what is the basic difference between the Raman spectroscopy, between the IR spectroscopy, what is the cause of the Raman spectroscopy, and what is the cause of the IR spectroscopy. Don't confuse it. The cause of the Raman spectroscopy is the change of the polarizability, and cause of the IR spectroscopy is the change in the dipole moment, and that is the basic difference between them, and they are complementary to each other, because the Raman spectroscopy, we don't need a permanent dipole or we don't need an induced dipole, rather we need induced change in polarizability, and that will lead to give us the Raman scattering light. So we can also from the Raman scattering light we can use the Raman spectroscopy as a tool to study the structure, vibrational structure, rotational structure of a homonuclear like H2O2 N2 molecules. If you like this video, don't forget to like this video, don't forget to share this with your friends, and don't forget to subscribe the channel. And we are so happy that we announced our online test series and your response are huge. So we are going to arrange this online test series on 16th August. So prepare well. All the best. Thank you.